So starting with the vertical line test. Now this is a test that determines whether a particular equation or a particular graph is going to be a function or not. So if a vertical line cuts a graph more than once, then there must be at least 2 points on the graph that have the same x coordinate. Now have a look, guys. The vertical line test simply uses a simple vertical line drawn on a graph. Okay? Now if it cuts the graph more than once, then it will not be a function. Okay? Therefore the graph cannot represent a function. Now the reason for that is a function must also only have one x coordinate. Okay? So have a look. It says must be at least 2 points on the graph that have the same x coordinate. So for one x coordinate, it must have one y coordinate. That's what a function represents. If one x coordinate has 2 y values or more, then it's not a function. That's why we use that vertical line test. And I'll show you more about that very soon. Now, if a graph can be cut by a vertical line in one point only, then the graph represents a function. Okay, so if you cut it with a vertical line and it's only one point of intersection, then it will be a function. And in 2 or more points, then the graph does not represent a function. Okay, so as I said, if the vertical line has 2 or more points of intersection, then it will not represent a function. In that case, we call it a relation. Okay, but don't worry too much about relations for now, only worry about functions. So this is the vertical line test. Let's try some questions related to this one. Starting with question 1, state whether the following graph represents a function. And they give you a graph, so I'm simply going to use my vertical line test. So simply draw a vertical line just like that, okay? And try drawing it in other places as well, like here, or here, or here. Just draw it anywhere on the graph. Do you think any of those vertical lines touch the graph more than once? See how they all have one point of intersection for the graph, with the graph and the vertical line? Therefore, there is no vertical line that can be drawn to cut the graph more than once. There's only one point of intersection for each. It only touches the graph once. Therefore, the graph represents a function. Does that make sense? Okay, that's all you need to do, guys. Just draw a simple vertical line and you'll see whether it's going to be a function or not, just like I did here. Okay, only one point of intersection. That's all there is with this test. So question 2, state whether the following graph represents a function. Simply draw a vertical line down the curve, and as soon as you draw just one vertical line, you can see that this vertical line has 2 points of intersection, which means it is possible to draw a vertical line. I drew a vertical line that cuts the graph more than once. Now we don't want to have the line to touch it more than once. We only need it to touch once. So therefore this graph does not represent a function. It's not a function because the vertical line test is not succeeded. Okay, there's more than one point of intersection. That's why. Okay. Question 3, state whether the following graph represents a function. So it's the same question but with a different graph. Now just draw a vertical line, guys. Okay, and try drawing it in other places as well if you're not sure. Draw it in other places, just any vertical line. And you can see that all of them have, each of them have one point of intersection with the graph. Okay, now you should notice that this graph is discontinuous. Okay, see how it's got asymptotes here? So it's discontinuous, but all we need to worry about is that vertical line and whether it touches it more than once or not. So it is not possible to draw a vertical line that cuts the graph more than once. Okay, so basically this graph doesn't cut it more than once, it only cuts once, therefore it represents a function. Okay, so very, very simple. Okay, question 4, state whether the set of ordered pairs represents a function. Okay, so we've got some pairs of coordinates. Now what I'll do is, this is my axes, I'm just going to plot it in, okay, to see what the points look like. So I just put it in like that. 0, 2 is there, 1, 3 is there, 2, 4 is there, 3, 5 there, 4, 6 there. Just plot it, okay? Not a big deal. And again, just perform your vertical line test. So what I'm going to do is put a vertical line for the first point, and you can see it only touches once. Second point only touches once, only once, only once, and only once. So each vertical line, because there's only one point in each position, the vertical line only cuts each point once. Therefore, it's definitely a function. Okay, just by looking at your points, it's obviously going to be a function. Okay, so that's what it is. Question 5, okay, again we're going to use the vertical line test. Simply put it down. That's my vertical line, and you can see it cuts only once, therefore it is a function. Okay, and you can see that if I put vertical lines in other places, it will still only have one point of intersection, so therefore it will definitely be a function. Okay, so that's the whole idea. Question 6. Okay, again, let's try putting a vertical line through this graph. I'm going to put it there, and this one has 1, 2, 3 points of intersection, which means it's definitely not a function. Okay, we only want one point of intersection for it to be a function. Okay, so this one's not a function. Okay, determine whether the following equation represents a function, and they give us the equation y equals to 2x plus 3. Now, as I said, we want to perform a vertical line test to determine if it's a function or not. So it's a good idea to start by drawing that graph. So you should be able to know how to sketch the graphs if you're given the equation. So that's my graph. And all I did was find the x and y intercepts. I don't want to go through all this because we've done a lot about drawing graphs, haven't we? So if you don't know how to draw graphs, make sure you look at that video on graphs first of all. Okay, so all I did was find my x and y intercepts by subbing in x is 0 and y is 0. You know how to do it. So my y-intercept's 3, my x-intercept is -3 on 2, and I simply join it to get the graph. Now I'm going to perform my vertical line test. So put a vertical line through the graph like that, and you can see there's only one point of intersection, which is excellent. That is definitely going to be a function. Okay, so this one is a function, this line here. And try putting vertical lines in other positions as well. Obviously, I think you can see that it's only going to have one point of intersection in any point on the graph, right? So this one is a function. Okay, and it's easy once you draw the graph. Question 8, determine whether the following equation represents a function. Now x equals to 4, how do we sketch that, guys? Just like that. X is 4 is here, and remember if x equals to some number, it's always going to be a vertical line. So I drew a vertical line at 4. Now I'm going to simply drop a vertical line on that graph. So if I put a vertical line, it's going to actually cover the graph because they're both vertical. Now guys, what do you think here? I drew my vertical line and it just completely covered the graph. Do you think it's going to be a function or not? How many intersections does it have? Well, I can tell you that it's not a function because this vertical line, well, the vertical line test line that I just drew on top, the yellow line that overlaps the x equals to 4 graph, it touches the graph infinite number of times. Okay, so some people think that it's only touching it once, so it is a function, but that's not true. This vertical line touches that graph in infinite number of places, so all of the places the vertical line touch. So more than one, definitely more than one, probably more than 1,000 positions. So therefore it's not going to be a function. Okay? Okay, so y equals to -2, so that we're going to determine if that's a function or not. So again, sketch the graph. And now because y equals to some number, it must be some horizontal line, just like that, at -2. That's going to be your graph of y equals to -2. And simply drop a vertical line and you can definitely see there's only one point of intersection. And in any other positions, it's only going to have one intersection, so it is definitely a function. Okay? So I hope this is getting much more easier. It's nothing big. Okay, this time we've got y equals to x squared. That's your basic parabola. You should be very, very used to. That's my parabola. And drop your vertical line and you can see it only intersects once. And same applies for all the different parts of the graph. Therefore it is a function. Okay, so simple, you should be getting quicker and quicker. State the following of the graph. This time it's a little bit of a different type of question. It says the permissible x values. Okay, now with functions it's important for you to determine what the permissible x and y values are. Now you're probably wondering what permissible x values is. Basically, permissible x values are possible x values that represent the graph. Okay, so this is the graph, and what are the x values that represent this graph? So have a look, guys. This point here is the end of the graph, and it just continues on and on. So this point here is 2, so it's going to be 2. Yeah? Now, there's no graph that's on this part of the graph. The graph starts from 2. Okay, and I'm worrying about only the x coordinates because it's asking for the x values. So the graph starts from 2 and it goes onwards forever. Okay, it's going to go on and on and on. So therefore the permissible x values are x is greater or equal to 2, because that point there is equal to 2, so it's including that point. So x is greater or equal to 2. That's your permissible x values. Okay? Now B, we need to find the permissible y values. Okay, so this time we look at y. Now y values, we'll look at the y-axis. So what y values will represent the graph? Now as you should already know, guys, this graph continues on and on. It just continues on and on like that. So it's just going to go wider and wider and wider forever. Okay, so what do you think the permissible y values will be? If it goes outwards on and on and on, meaning it will go like that forever, it will eventually represent all values of y. So because, have a look, guys, the answer is all real values of y, so just write it as all real y, that's fine. Now as you can see, well, just by the given graph, it's from this point to this point. So a lot of you may be just thinking just this part, but as I said, it continues on and on. It continues on and on until forever. So it's going to be representing the whole y-axis. Okay, so I hope you understand what I'm saying there. So it's not just that part there. Okay, just remember that the graph continues on and on forever. That's why all the values of y represents this graph. Okay, that was 11. Let's look at 12. Now we're going to do the same thing with this graph. It says the permissible x values to start with. Now this time, guys, this is like an exponential graph. Again, you should be used to this because we've done this before. Yeah, my graph is very close, so I did it very detailed. So it's actually touching the asymptote, but it shouldn't. Just make sure that this graph, it shouldn't be touching the asymptote. It just looks like it, but it's actually not. But we've got an asymptote. And remember, guys, this graph also continues on, and this part, it also continues on and on. But it will never touch the asymptote, but it will always be tending to it forever. Okay, so on both sides, it's going to continue. So what do you think the permissible x values are? So have a look, guys. Because this graph continues on and on, all this part of all these x values would represent the graph, and same with this, all this part and forever. So what are the x values that we're going to be having? All real x, all real values of x represent this graph. Okay, or the graph represents all real values of x. Okay, that's the idea. Hope you understand what I'm saying. Okay, guys. Now that was A, so make sure you understand that first. Try to sketch it on your paper by yourself and see if you can understand what I'm saying, because this is very important. Now for B, the permissible y values. Now, look, guys, the graph does not have no part of the graph is below -3. -3 is the minimal point of the graph, right? It's the smallest value of the graph. Now it's going to go from -3, it just continues on and on and on. So what do you think the permissible y values are? Well, it's going to be y is greater than -3, but not equal to -3. It's just greater than -3 because this is an asymptote. The graph will never touch -3. It will always tend to it, but never touch it. So it's going to be greater than -3 because the graph is just continuing on and on forever from that point -3. So that's the permissible y values. Get it? Hopefully. So that was 12. Now 13. Okay, again, we've got this kind of graph. We need to find the permissible x values. So what I'm going to do is have a look at the graph, and as you can see, guys, this graph, it just goes on and on and on and on. So all these values of x will be true until forever, and same with this side, all values of x forever, except this point here, because this is an asymptote. The graph will never touch that asymptote. The graph tends to the asymptote but never touches it. So this point here is the only point where the graph doesn't touch. So the answer is all real values of x, but x can't be -2. X cannot be -2 because of that asymptote. Okay, but as you can see, all these other values of x, okay, represent the graph, except for 2. So this is how you should write it. Okay. Now that we've done that, let's look at the permissible y values. So the y values are the values of y that represents the graph. And as you can see, now because there's a x-axis here, you can't actually see the dotted lines, but remember there's also asymptotes here. So this is actually a hyperbola. You should recognize that name. The hyperbola has two asymptotes. So one that's horizontal and one that's vertical. So again, can you see that if this graph touches the y, has the part of the graph represent all these values of y forever, and this part of the graph represents the y, should be like that, right? All these values of y forever, okay? Except for here, this asymptote. It doesn't touch that asymptote. So it's going to be all real values of y, but y equals to 0, because this horizontal line here is actually y equals to 0, isn't it? So except for y equals to 0, all values of y is true. That's what it means. I'll just rub this off so you can see. Does that make sense? It might be a bit confusing for some people, so make sure you're understanding this before you move on. Okay, that's the answer to question 13. Look very, very carefully. Now this time it says find the permissible x and y values for the following. We're going to do the same thing, okay? So starting with my permissible x values. Have a look, guys. Now, the graph represents x values, these x values, and again it continues on and on, so it's going to have x values forever, and same on this side, it has x values forever and ever because of the graph continues. So therefore the permissible x values is all real x, all values of x. Okay, what do you think for y, guys? Think about it. Well, have a look, guys. Well, because this graph continues, it's going to represent that y value, 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 and this y value, all these values of y forever. So therefore, permissible y values is also all real y. Okay, all real values of y. Okay, so there's no restriction here. Get it? Find the permissible x and y values for this graph. Okay, it's a parabola. So we'll start with our permissible x values. Guys, again, you should know that this graph just continues on and on like that. So represents this x value forever, x value forever, all these x values, and same on this side forever. So all values on that x-axis. So therefore the permissible x values are all real x. Okay, so you should be understanding what I'm saying by now. And then what about the permissible y values? Now guys, they actually give us the coordinates of the vertex, which is -3, 9. So that should be -9, sorry, because this doesn't make sense if it's +9, is it? So that's -9. Okay. So the graph goes upwards. So it's simply y is greater or equal to -9, because that point there is -9, so we're going to include that point. Okay, so we're going to include that point -9, and anything above that is where the graph lies. So all the y values are these y values here. All these values that's above -9. So that's the answer for the permissible y values. Okay, so yeah, make sure that's going to be -9. It's a little bit of a mistake. Now 16, find the permissible x and y values for this graph. Okay, so I'm going to start by finding my x values. Now this graph so when we're looking for our permissible x values, we'll only concentrate on the x-axis. And this is our x-axis, and the graph only starts from here and ends here. So the graph is only between -3 and 3, so the permissible x values are x is greater or equal to -3 or less than or equal to +3. So x is between -3 and 3 basically, and including. Make sure you have the equal to sign because the graph is also on -3 and 3, so it's including those two values. Easy, isn't it? This one's easy. Now what about the permissible y values? Well, the graph, we'll only look at the y-axis for this one. The graph starts from here to here. Yeah? So this point is on the x-axis, which means it's 0, and this point is 3, so therefore the y values would be between 0 and 3, and also including them. So y is greater or equal to 0 and less than or equal to 3. Okay, must be including those 2 points.